Yeah, we are all ready, Dr. Ahmed. Yeah, please go ahead.
Okay, welcome back, everyone. We are going to start the day today with a panel discussion with a very important topic, quantum computing use cases in chemistry, quantum simulation, finances, and quantum AI. Our guests, who are actually our friends, are Dr. Asma Safan. Dr. Taha Slim is a moderator and a speaker too, a panelist. Engineer Ahmed Salim, Alain Chancey, and William Slater. Dr. Taha, if you like to make any introductory remarks, because this topic is really very important. It is the use cases. Everybody is talking about quantum, and everybody is talking about the use cases. And whenever we talk about the use cases, the speakers always indicate that we still don't have an advantage yet, a quantum advantage that we're looking for. On the other hand, decision makers and domain experts who are not quantum people are always looking for the advantage. They want to see what they pay for, and they don't want to pay for it today and get some advantage next year or even tomorrow. They want to get what they pay for immediately. So I think this is going to be a very important session to discuss this issue or this dilemma, especially that we are talking in multiple fields, finance, chemistry, and other fields. So Dr. Taha, if you like to make some remarks before we start asking our friends, our panelists, to give us some insights about this issue.
Yeah, thanks, Dr. Ahmed. And I would like to thank again Cairo University for helping out in setting up this school, including Dr. Haytham, the Dean of the Faculty of Computer Science and Artificial Intelligence, and of course, Dr. Ahmed Shawqi Musa, who is the moderator also and the panelist among us. And thanks for everyone. This is today is the third day, and please continue attending because we have several use cases covering chemistry, finance, machine learning, and also cybersecurity. So stay tuned and follow up. So regarding the chemistry parts, always a dream to make an accurate simulations of molecular structure, and indeed we have seen it in synthesizing and also manufacturing vaccines and the medicine. Some vaccines we hear that they have to be kept in minus 20 degrees and so on. And the reason for that, the simulations and the experiments found out that the equilibrium structure will be stable at this particular temperature. Hence, the simulation is very powerful and it can provide very good insights. Now, with first principles, when we use quantum mechanics to simulate the molecules and the chemical reactions and the chemical formation, we want to have precisely the same image as what we see in the lab. So we can reduce the effort in the lab, and also we can reduce the workforce and the R&D effort. And for that, we want to use accurate simulations. However, when we use the first principles and the quantum mechanics, we always hit the wall of the computational complexity. The computations are very hard, and indeed they are resource intensive, so they take huge time and huge resources to compute, and hence we might sacrifice the accuracy and the precision of the model because we have to use approximations. And this problem appears with large molecules. We cannot fully simulate the DNA because we are talking about hundreds of species inside. And when we want to treat the interactions between the different parts of the DNA, we are talking about millions of interaction channels, and that's translated into equations and a very big sized matrices that sometimes they are trillions by trillions in size that have to be solved. Richard Feynman and other physicists envisioned that maybe with quantum computers we can use quantum systems to simulate other quantum systems, and we can reduce this computational complexity that appears using linear algebra and also differential solvers. on classical computers. And the question becomes how we can use this and how we can utilize quantum computers. Still, quantum computers are in early stage. However, the current progress, and for first time, as we are going to see later today in the panel, in the last panel, the companies and startups are working in showing the computational advantage in chemistry, and chemistry is very promising field. And indeed, if it worked with fault-tolerant quantum computers, when we have large number and enough numbers of qubits and good error correction mechanisms, then we will be able to simulate very, very large molecular structure and get insights about chemistry and the physics more than what we have before. And that hopefully that will be the case. And then I can ask you, Dr. Ahmed, how do you, we can start then with you, how do you see the future of chemistry from HPC perspective, and in your opinion, how quantum computing can help easing this problem?
Actually, I was going to start by asking you a question. So it looks like we both are setting traps for each other, but I don't mind. Well, okay, let me answer first and then make a remark about something very interesting that you just said. Let me start with yours first. You mentioned that Richard Feynman actually spoke about this potential. And for the audience from different fields who may not really know Richard Feynman, he was one of the historical figures in the world of physics, and he died in 1988. Having said that, it is a clear evidence that the idea of quantum computers is not that new. So it was thought of at least before the time of Richard Feynman, since he spoke about it in his life. So I wonder, I really don't know how mature the idea was at his time, or how far they reached, but the idea was there. The idea of encoding information into a quantum circuit or into a quantum structure was there, not only for encoding, but they were talking about quantum computers. Now, to your question, Dr. Taha, I think quantum chemistry and quantum physics, I would say also quantum biology and the quantum biophysics, are the most promising areas for quantum computing. And the idea is simple. Today, we are trying to simulate physical, chemical, biological, or biophysical structures with classical high-performance computers. And this takes huge computation. You know that I think in the first lecture I gave, I was giving that example. I don't know if I went over this example or not, but it takes a petaflop computer, which is one of the top computers in the world. It takes about a year to simulate the molecular dynamics of a molecule of not that large. So a moderate or a medium-sized molecule, to get the molecular dynamics of that molecule simulated for 1 millisecond, only 1 millisecond, it takes a petaflop computer to run for a year. Now, we spoke about the fact that quantum computers are not expected to be superior to HPCs, and HPCs are not going to be superior to quantum computers. They will have to work together. But why in these areas we have hopes in quantum computers? Because they simulate that something that they perform themselves. It is the way they work. Unlike the classical computer, which is trying to simulate something outside of the physical structure and the physical mechanism of the computer. So here, if you want to simulate a quantum chemistry system using a quantum computer, which is running on quantum structures, I think that should be the most accurate and also the fastest. One day, whether that day is going to be soon or not, I don't know. I'm not good at making predictions or prophecies.
And so I think, thanks, Dr. Ahmed. That's very clear and also clarifies a bit that quantum computing won't replace the classical computing. And indeed, the idea when we back to the time of Feynman, they were envisioning even error correction, but they started to implement, and it took a lot of time to arrive to this case. And maybe we can start now with Engineer Ahmed Salim. Since now almost we have about 50 or 55 years passed since the Feynman's famous lecture about the quantum computing. Indeed, he was not the first one because there was a lot of other people who already before him. I tried to feature them in a video on YouTube. But now, reflecting back, how do you see the quantum computing now, especially at what you see from the progress in IBM and as IBM quantum ambassador, and also a quantum advocate in general, comparing to the initial idea?
Thank you, Dr. Taha and the team for your time and hosting me today. So when it comes into the chemistry and the quantum, let's think about the HPC and where is the HPC is excelling and where it hit the walls. And I think in this part, we'll start thinking about the quantum as well to continue the work or carry out what is beyond the limitations of the HPC, okay? So in principle, we cannot see that cannot say that the HPC is obsolete or something. No, it's a complementary component, essential component when it comes into building the quantum ecosystem, let's say. So the HPC, I think it will reach some points of limitations when it comes into the exponential complex of the chemistry problems. And this is actually the need a different type of processing where we can avail it through the quantum machines. Okay, so the powerful computational power that we are getting from quantum computers definitely complement what the HPC is trying to do or trying to achieve. And if you look into IBM and even in the roadmap, we see that the HPC, it's an essential part of the quantum processing units. And as you know, there is a lot of algorithms that IBM announced in the market, which has the HPC working hand in hand with the quantum computer, because we need the best of two worlds. HPC is working on the classical way of processing, and the quantum is using or utilize the quantum physics principles to be able to do much higher computational power. The problem in the quantum, as we know, it's not reversible. Once you start your processing in the quantum machine, you cannot stop it. You cannot do a recursion or a loop or something like that. That's why IBM thinking that the HPC will complement this part. And if we look into IBM roadmap, we have the recursion, the circuits on the Qiskit toolkit, which is the programming language that IBM is using for modeling the problems and put it in the quantum machine for processing. So if we look into it, we have, for example, let's give you an example, the SQD. SQD as an algorithm, it's a sample-based quantum diagonalization. It's working between the quantum machine learning, quantum machines and HPC, along with the GPUs. So we have three main players. Maybe if we classify it as quantum and the classical, so we have now two components. It's the CPUs and GPUs, which belongs to the HPCs, and we have the QPUs, which belong to the quantum machines. So if we look into this algorithms, we can see that it starts with a classification, preparation, optimization on the HPC. Then we'll start the calculation on a quantum computer. And when it comes into the processing, we'll come back to the HPCs. So as we can see, the HPC and the quantum computer working hand in hand to be able to deliver a value. And many publications that IBM has did and in the chemistry, for example, and it's published on Nature and the archive, where we are able to do a modeling for some molecules even with the quantum noise that we are experiencing now in the quantum machines. and we are able to announce that the quantum fault tolerant quantum computer, it will be like 3-4 years from now. So in my point of view, the future is promising when it comes into building a heterogeneous system, collaborating or jointly between the quantum machine and the HPC.
And that's really great. Thanks, Engineer Ahmed. Perhaps Dr. Ahmed would like to ask the next question.
Yeah, actually, we wanted to have this. This panel is going to be like in diverse fields, multidisciplinary. So I would like to ask Dr. Asma, since she's going to give us a talk and a tutorial on the applications of quantum computing in the financial industry. How do you see the future of quantum computers in finance? Right now, we think that the most threatening application of quantum computing is to finance and military, which is by breaking passwords and breaking the security system. Do you think this is the only threat or the only opportunity, or do you think the applications of quantum computing in finance is going to be more than that? Oh, you are going to give us a
no,
talk
I
on
show
5G.
you one slide to show what I need to say. Okay. Thank you. First of all, thank you for this valuable discussion panel. And I'm talking, if we want to talk about quantum and finance, so the promising finance stages will come through 6G networks, 5G and 6G networks. As we see, the 5G network is playing a promising game in the industry today. But what about if we are migrating to 6G network? So the migration from 5G to 6G needs a quantum computer. We need to intersect between the quantum and the next generation wireless convergence. But I think in the first stages, I think quantum will not a replacement. It will be inside the classical solutions or classical traditional computers, but the quantum will fill the missing layer. Sorry. The missing layer that makes 6G is possible more than 5G. If I'm talking about the promising finance in this field, I'll talk about if we can integrate in the wireless network the quantum optimization, quantum security. If we make the brain of the core network related to quantum computing, it will take a precious timing that we need from GPS. We can overcome eavesdropping or trying to spoof the GPS. We have many problems related to 5G that we can overcome using quantum plus 6G networks. So at last, I need to conclude the advantage of using quantum computing in 6G networks. If we are using quantum optimization related to something in our network called the radio access network, or in routing, or in cloud scheduling, changing the hardware to virtualization, and put the function inside the cloud. Also, we will overcome most of our security issues, like attacking using quantum computer. We can overcome this using PQC, and also we can secure the link between transmitter and receiver using QDK, as Engineer Ahmed said. Also, we can make the intelligent brain or intelligent core using quantum machine learning inside the next wireless generation networks. Also, as I said, timing precious, synchronize all the base stations. So we can use many use cases like ultra low latency and reliable applications like remote surgery, like automated driving. All these can be done the dream can be achieved using quantum and 6G as they converge with each other. Okay.
Thank you, Dr. Asma.
Thank you.
Very insightful, very informative. Dr. Taha?
So now we come to Bill. So Bill, the main motivation for going for the quantum cybersecurity and especially for PQC and post-quantum cryptography is the fear of the Q-Day. And of course, there is a lot of hype about the Q-Day, and that has been hyped or like hype-ish all the time. So what's your perspective about the Q-Day and what the real value of quantum computers would come when it comes to this mythical Q-Day?
Sure. Q-Day is coming whether we like it or not, and the regular announcements about latest developments in quantum computing, to me, just kind of firm it up that that day is getting closer and closer. And now CISOs and CEOs are starting to pay attention. What's interesting is that the two areas right now that are paying the closest attention to Q-Day are the heavily regulated areas like finance and government. And they've appointed leaders, which ironically is usually not the CISO. It's often the CIO or the CTO to take charge responsibility for these projects. And they're giving these people budgets. What's freaking people out is that these projects take a long time, 3 to 7 years in some cases, and in some cases 7 to 10 years. And if we think Q-Day is going to be here in 2029, inevitably it's going to happen that people have ignored how long the projects take, and so they're going to get caught up short. And I put links to a presentation that I just delivered last night. What a HNDL, harvest now, decrypt later attack looks like, because I showed two examples of data that was thought to be sent in secrecy, the Enron email data set, and also this longevity expert that got terminated last month when his name came up in the Jeffrey Epstein files that our Department of Justice revealed. So now people are waking up and realizing that this is a serious thing. And myself and other strong people in the industry have kind of like we had a legendary figure in the American Revolution named Paul Revere, and it was his job that if he figured out the British were coming by sea, he was they had light signals. If they're coming by sea, do this. If they're coming by land, do this. And so he went through all the towns up in Massachusetts and was alerting people that the British are coming. So I'm in that group of people that, you know, quantum is coming, Q-Day is coming, and you better get ready for it. I think it's an unfortunate thing, because I think there are many more uses for quantum computers other than breaking ciphers. very few people are smart enough or work hard enough to become full professional cryptologists. But there are so many problems that we've already discussed that we can solve in chemistry and simulation and modeling that are, to me, much more meaningful than breaking ciphers. It's also a negative cloud that I want people to realize it's out there and it's a danger, but I don't want our, quantum computers to be synonymous with breaking ciphers, because that's kind of a dark cloud to put over quantum computing. So I have a balanced view. The other thing I'll say, when people download my deck that I put out there in the chat, please go out and look at slide 57, because my growth, I've been attending these meetings since 2017, and now I'm up to about 6 to 8 of these meetings a week. Do not be geographically centric. Don't be Cairo centric. Attend meetings in the U.S., attend meetings in Germany, Philippines, where else? Australia. Attend meetings all over the world and get to know these people, because the more you're exposed to this stuff, the more your learning curve will go up and the more productive you'll be. So I invite people to stay in touch with me. I love to talk about this stuff and write about it and present on it, but just don't, you're here, don't just be Cairo-centric, be international.
Yeah, thanks, Bill. Yeah, Dr. Ahmed.
Yeah, thank you very much, Bill. Our next question is for engineer Dr. Alain Chancey. It is about the area of quantum AI, and this is a complex one, because nowadays we are trying to get quantum computing into every possible application. And AI is nowadays it has gone already into every possible application, almost all fields. So when we get quantum AI, how does that work? So you try to implement artificial intelligence with quantum technology to be used in every other technology. Isn't this kind of quantum computing still? Or are we focusing here on the issue of implementing machine learning and deep learning or learning techniques using the quantum technology? Can you clarify or give us your insights about this complex relation between AI and computing in general?
Oh, thank you. This is a very wide question. So I'd say, first of all, people think about quantum machine learning, but and traditionally it is there are four. It's divided into four: whether the input is classical or quantum, and whether the AI is processed classically or quantumly. Okay, and there are big differences there, because potentially the most powerful application of AI and quantum is to process quantum data, typically coming from quantum sensors, directly with quantum processing units. Okay, so that's an example. The other thing, recently there was a brilliant paper by John Preskill and Robert from China about an advantage for processing large amounts of data. It's called actually quantum learning. That is to say, the idea is to learn from massive amount of data, but the data is processed once and then thrown away, because one of the big challenge with quantum computers today is we haven't got the equivalent of random access memory. Okay, conceptually you can talk about QRAM, but it's not available. So so the bottleneck is still today with loading classical data into a quantum register. But of course, if we are talking about processing directly quantum data, there is no such issue. The other thing I'd like to mention, another very exciting combination of AI and quantum is actually combining quantum sensing, quantum sensors, with AI agents. AI agents are becoming ubiquitous, and they are very, very powerful because it means it's not just processing data. It's actually it can power robots and drones and that kind of stuff. And I'd say that AI agents combined with quantum sensors, that is something which can be done today with available technology, and that is potentially something which can be much more impactful than the traditional view of quantum machine learning. A recipe for failure is to basically try and cast classical methods into the quantum world. No, the good approach is to think creatively using a paradigm which is basically classical quantum hybrid workflows. And in that classical quantum, HPC quantum, AI fits very well in different places. So that's my try to attempt to clarify and open new doors at the same time.
Excellent. Thank you very much.
Yeah, thanks, Alain. And then we go to the next question, which is about quantum finance. So recently, IBM, in collaboration with a famous bank, already announced a very nice use case about utilizing quantum computing and showing the potential advantage of quantum computing in that arena. So what are the main challenges in finance? Of course, we are going to have tomorrow a session about that, but it will be great to have a heads up about what are the main challenges in quantum finance and how quantum computing can contribute in solving part or maybe all of them. Yes, question for Engineer Ahmed Salim.
Okay. Okay, very interesting question. Finance, it's a very critical like industry. It hits the people, money, they're planning for the future as well. And as you just mentioned, we found out that IBM collaboratively with HSBC Bank in UK, they were able to make a good prediction for the bond prices. I think, if I'm not mistaken, the optimization or the enhancements reach like 30% away from the classical way of bond prices prediction, which is very huge if you look into the improvement in a financial sector. For example, if you have like a $1 trillion sector and you have improvement for 1%, imagine how this will be deployed on the larger scale and what are the benefits that people will get out of this. So if we look into the financial sector, we have many use cases that we can work on it. And even actually IBM is working with even the partners and the financial institutes across the globe to try to optimize the product pricing, the optimization for portfolios, maybe the highest income agents for the banks, anti-money laundering, credit line optimization. So a lot of use cases that we have in the pipeline. IBM is working with the partners, as I mentioned, the worldwide institutes, to be able to take it to the next level. The risk and the anti-money laundering, I think, two of the hot topics, and Will Fargo has published on archive some of this work, how to utilize the quantum machine to address and resolve these challenges and problems. Still, we are imagine that we have some breakthrough in this quantum noisy system. Imagine when we have reach the quantum advantage and the fault tolerant quantum computing, what are the benefits? I cannot imagine even the life in this sector, especially, and this is actually related even to the cryptography. So it's it's a crazy now the crypto ecosystem and all the cryptocurrency that we have, it's running in the distributed network. And if we correlate it with the quantum cryptography, I think we don't know what will happen in the future, but this is required a lot of attention when it comes into building the products from now and to be ready for the quantum day.
Yeah, thanks a lot, Engineer Ahmed. Dr. Ahmed. Yeah, Dr. Ahmed, you are muted. Yeah.
Sorry. Thank you, Engineer Ahmed. I want to put a question at large to our panelists altogether, if you have any insight. I'm just repeating my thought that I started with. We are all seeing a great promise of quantum computing to solve many problems, give the advantage or the supremacy or whatever we are expecting from quantum computing. But what is it that can be used as a selling point for right now, if any? Should I rephrase it, or is it clear?
Yeah, perhaps it could be great with a bit of rephrasement.
Okay. If we want, let's say, play the role of the IBM now, if you want to sell a quantum computing solution to any industry right now, what would be your selling point? Especially if you...
Yeah, you want to mute Dr. Ahmed again. Yeah.
I didn't touch it. I don't know why I got
Yeah, that one,
anyway,
sometimes the teams.
Yeah, let me restate this. Suppose that we are playing the role of IBM right now, trying to sell a solution to any industry. We want to pick up any examples, not specific one. And you want to make a selling point where you are facing a customer who is resisting to pay for something with no benefit, with no immediate benefit. The benefit is mainly for the future. How do you tackle this problem?
Very tricky question. We are facing it on daily basis because it's still all under the research, what we are trying to achieve in the quantum, and you cannot like give an open promises and confirm it that if we will do this, we'll reach in this, move from this point to that point, because still in the quantum world, the uncertainty is the boss. So when we approach to a client or the customer, even in the financial, because it's a very critical, as I mentioned, the critical industry, we don't just telling, okay, we will run these algorithms in a faster computer. No, it's a different angle. We are telling that we can make the quantum computer help you get a better financial decisions. So it's not a matter of I will give you a final results. Maybe I can give you a better or a different way of thinking, another look into the problem from a different angle, where it will give you, beside the current or the traditional ways in the financial sectors and running these traditional problems that we are tackling right now. I will combine all these plus the advantage of the quantum machine to give you a better financial decisions. And it's shifting not just the performance, it's the economy and the progress that we are seeing in the quantum machine, and with all the use cases, the success that we can see in the quantum use cases that we are achieving right now. It's promising, because whoever will not start now, he will be behind. Once we have the full advantage, I can imagine that it's a matter of orchestration between the current and the traditional tool that we are using, plus moving to the quantum era, where it has like a hybrid approach between the classical and the quantum to be able to get a good conclusion to the problems that we are facing right now. So we are trying to move from the approximation to modeling to make it more trust. Okay, so it's not like an open conclusion, or maybe a solid conclusion that we are telling the customer, if you will do this with us, you will reach to this much of maturity. We'll start doing the research, utilize whatever we have. Maybe this will lead us to invent a new way of tackling problems or solving problems. And this is another value that we can work with the client to have intellectual property in IP, and we can announce this. So it's a mutual benefit between IBM and the client. And the most important part, the experience and upscaling the current capabilities that we are dealing, or when we have a consortium between IBM, business partner, and the client.
And if I may add to this, that's also a brilliant answer indeed. It's challenging, and from hardware perspective, the main selling point is also for students to learn. So a lot of startups in quantum hardware, they sell a complete unit like in photonic or ultra cold neutral atom or trapped ions, all of that to universities as well. So the universities and the university labs are main customers at the moment for major startups. So they are making most of the money, presumably, according also to my view, that's to make a disclaimer here, from selling chips and calibration devices to universities. So from a hardware perspective, so the one can offer the service via the cloud, they can make money from the usage via the cloud, and the one that they don't have access to the cloud, they just sell hardware component.
I see. Very interesting. So I'm just glad to hear that IBM is facing the same challenge that we are facing.
Yeah, no pressure, Ahmed, on you for in the sales. No pressure. You have to sell 10 quantum computers per day, you know.
Yes.
Yeah, we're looking for the day when we have quantum smartwatches, quantum mobile phones. Okay, I think we are on time to end this session if we don't have other questions. Do we have questions, quick questions from the audience before we start the next session?
Yeah, Bill has a question. Yeah, please go ahead, Bill.
Yeah, for all the young people on the call, I kind of had this revelation this week where I've been in computing for a living for 49 years, and I did it for 4 years in college before that, so 53 years. And I was thinking about the kind of those of us who are old enough to remember getting a fast computer. My fast computer was 4.77 megahertz when I got my first computer. It was, I don't know, 1985, so going back 40 years. My first, I was doing mainframes at work, but I was doing PCs at home, and that was a lot of fun. But what's interesting that I'd like you guys to think about is that it used to be kind of like a big deal. You know, if your neighbor got a 33 megahertz computer and you got a 50 megahertz computer, well, a lot of people thought they were better than their neighbor if they had a 50 megahertz computer. Now, it really doesn't matter how fast your computer is, thanks to things like artificial intelligence and the cloud. And I invite people to go back and look at the presentation that I put out there, because the room was just knocked out last night when I showed 3 simple ChatGPT prompts that would go off and kick off a lot of work for you in your PQC project. And there's even a command that I put out there for drawing a 25 qubit quantum computer circuit for working on Shor's algorithm. So the point is, we've come back full circle, where now it's not so important about the processor inside your laptop or your workstation. Now, if you're smart, you can have a slow computer and offload the work into the cloud and get the results back, and all of a sudden you're smarter and more productive than the guy with a faster computer than you. So I think this is really encouraging times to be in, because it really doesn't matter how fast your desktop computer is.
Yeah, indeed. And if I may add, people always worry or think about speed when it comes to computers, but let's keep in mind that it's not only about speed, it's about realistic computation. Like, for example, there is a whole class of methodologies of solving scientific problems by generating random numbers of certain distributions, which we call Monte Carlo method. And when you do that on the HPC or the classical computer in general, recall that you are generating random numbers with an algorithm. So they are not really random. We call them pseudo-random. But with quantum computers, if you want to get realistic random number generation, then this is, even if it turns out to be more expensive or slower, it is your only bet, especially in quantum chemistry, quantum physics, quantum science in general. If you want to generate realistic random numbers to simulate those physical systems, then your quantum computers are your only bet, because this is the nature of their work. They work probabilistically. On the other hand, the deterministic computation done by HPCs, using it, you just try to do pseudo-random number generation, but it's not truly random number.
Yeah, there's definitely the case. Yeah.